All right, guys, this is our final lecture for statistics, and it's all about chi-square. And as you will see, chi-square is very different from what we've been doing so far. We're still going to be using the 4 steps of hypothesis test, but the calculations and the meaning of the calculations are going to be very different from what you're used to. So as they'd say in Monty Python, now for something completely different. All right, topics. So, I'm first going to introduce you to the difference between parametric and non-parametric tests. Everything we've been doing so far were parametric tests. Chi-square is a non-parametric test. Then I'll cover the very simple and few assumptions of non-parametric tests. Then I'll show you how you can take data that's initially designed for a parametric test and convert it into data that is acceptable for a non-parametric test, and some of the reasons why you'd want to do something like that. Then I'll talk about the difference between the chi-square test for goodness of fit and the chi-square test for independence, and then I'll show you the formula, how to interpret the formula, and then we'll do plenty of examples to make sure that this stuff makes sense to you guys. All right, parametric versus non-parametric tests. So before, we were doing parametric tests, and parametric tests require that you have a numeric score for each participant, and you typically use the means or the sums of those scores to do your hypothesis testing, with the exception of ANOVA where you use the variance, but then for Tukey's Posthoc Analysis you're using the means. So you have to have the raw data that gives you the score for every person in your study to do a parametric test. Also, those scores typically need to be in an interval or a ratio scale. There's types of correlation analyses that you can do with nominal or ordinal data, but for the most part, to do a parametric test, you need to have data that's on an interval or a ratio scale. And technically, those other types of correlations that I didn't get to are forms of non-parametric tests. Okay. In parametric tests, you're also using sample statistics, like the mean, to make inferences about population parameters. So, using the mean from the sample to make inferences about the mean in the population. Now, non-parametric tests are also inferential statistics, using samples to make inferences about populations. But again, we're not going to be using all the numeric scores in non-parametric tests, and we will not be calculating means in non-parametric tests like we used to do for parametric tests. Okay. Also, the parametric tests are really only accurate when certain assumptions are met. So, for example, the t-independent measures assumes that all the data come from a normal distribution and that the population that's being compared has the same variance. So remember the homogeneity of variance assumption. T-independent measures also assumes independence of samples. Well, sometimes those assumptions will not be met. Sometimes you won't have data that comes from a normal distribution, and you won't have a large enough sample to achieve a normally distributed sampling distribution. So, there's very few assumptions with non-parametric tests, and so sometimes it's easier and more accurate to do a non-parametric test than a parametric test. Another problem with parametric tests is when you have data that's highly variable. So when you have a really large standard deviation in your population, or a large standard deviation in your sample that tells you that you probably have a large standard deviation in your population. So whenever you have a highly variable data set, you're going to have a really large standard error, because a larger variance in the numerator of the standard error gives you a larger standard error, if you think about the majority of the test statistics that we calculated this semester. So when you have a highly variable data set, it's going to be more difficult to reject the null hypothesis because your standard error is going to be way too large. In ANOVA, if the error in the denominator of the F statistic is really large, then the overall test statistic is going to be smaller as well. And again, smaller test statistic, not likely to exceed the critical value, difficult to reject the null hypothesis. So, highly variable populations and samples aren't necessarily a problem in non-parametric tests because it doesn't look at the raw data for the numeric scores for each study participant. It takes that raw data and converts them into frequency-based data that we put into different categories. And this will make more sense when I show you some examples. You can also use scores that are on a nominal or ordinal scale for non-parametric tests. Or you can use data that's on an interval or ratio scale, and all of those can be turned into frequency-based data. So again, parametric tests, looking at raw scores, Nonparametric tests, we're essentially counting how many people fit in each category, and the category is based on the various values that can be found in our data set. Again, that'll make more sense when we do an example. So with nonparametric tests like the ChiSquare, you're using sample frequencies and proportions to make inferences about population frequencies and proportions. So we're not using the mean for the sample to make inferences about the mean in the population. We're using the proportions and frequencies in the sample to make inferences about the population proportions and frequencies. Proportion just tells you the amount of people that fit a certain category. The frequency tells you the number of people that fit a certain category. Also, with nonparametric tests, there are very few assumptions, which is a great thing. Remember, before I was telling you we had to have a normal distribution to do hypothesis testing with the types of statistics that we've learned about so far. That is not an assumption of nonparametric tests like the chi-square. Some of the assumptions that do have to be met, though, are independence of frequencies. So each observed frequency, or each category, is generated by different individuals. So in other words, no participant can be in multiple categories. You also need to have relatively large samples to do a chi-square. When the expected frequency under the null hypothesis, which you'll understand more about here in a little bit, is less than 5, then even a small discrepancy between the observed and expected frequencies can result in significant differences. So all you need to know for now, because you don't know what an expected and observed frequency is yet, unless you read the chapter, which I hope you did, all you need to know is that you need to have a large sample to run a chi-square. Also, large variances in data set, like I mentioned before, are not a problem when you convert scores into categories. It essentially eliminates the variance, so it's not a problem. So here are some examples of taking data that was originally collected for a parametric test and converting it into data that's appropriate for a non-parametric test. So sometimes the data that was collected with the intentions of analyzing it with parametric tests don't meet the assumptions for the test. So you can use the frequency distribution for the original data to place participants into categories, and then you can use non-parametric tests to analyze the data more accurately. So one example would be this single variable example. We're just measuring one variable. We're counting how many times that variable appears in our data set. Well, here we have a situation where we have a really high standard deviation in this sample. So if you calculate the standard deviation for this sample, you would find that it's 4.03. And the mean for this sample is 3.65. The standard deviation is bigger than the mean, so we have a really large standard deviation and a lot of variability. We also have a situation where we have an outlier here. So outliers and a high degree of variability create issues when it comes to calculating your test statistic, because our standard error would be really large, and even though we would have a difference in this case between our sample and some population, that difference would have to be huge to exceed the standard error. So we may underestimate the true effect of our independent variable, assuming that this sample experienced the independent variable. Because we have such high variability, our standard error is huge. Well, the same thing is happening here. This is an example where we have multiple variables. So this would be data that's originally designed for a correlation analysis, but we have a crazy outlier here, this 1515, and that's going to bias the correlation to appear strong and positive. But if you look at the raw data, you can see that X and Y are not consistently positively related. So if you calculate the correlation for this data, you would get 0.898. But that's not really an accurate reflection of the fact that here, this person has a 5 for X and a 6 of Y. Well, this person has a larger value for X, but they actually have a smaller value for Y. So just looking at those and considering that's half of our data set here, we've only got 4 people in our data set, it's not a clear positive relationship. But the calculation is biased by this outlier, so it's really inaccurate. So outliers are not an issue when X and Y are used to determine the number of people in each category. We're eliminating the effect of that outlier, that strong effect. So for the single variable example, here are the values of X, and I didn't include all the values between 0 and 10 just to make it simple. But that's how you would do it if you were doing a frequency distribution table to make a frequency distribution graph, if you remember from chapter 2. So here are all of our values of X. 5 people had a value of 0, 6 people had a value of 1, all the way down 7 people had a value of 10. Well, you can use the values of x to place people into categories. So let's say that we say that low represents anybody who had x less than 5. And usually there's some reason that we differentiate low versus high. But just for keeping it simple, low, x less than 5. So how many people had an x less than 5? Well, here's x less than 5, and all these are x less than 5. 3 plus 5 plus 6 plus 5 gives you 19. And then we say we will count somebody as high if they have a value of x greater than or equal to 5. 10 is the only value in our data set that's greater than or equal to 5, and 7 people have that value. So there we go. One way to check your work if you're doing something like this is to find the sum of f and make sure that it equals the sum of all the frequencies in your categories here. Now this multiple variable example, that's like a correlation, but this outlier prevents us from doing a correlation accurately, and we don't want to get rid of the outlier. So we're doing a nonparametric chi-square test to figure out if there's a relationship between x and y. Well, this gets a little trickier because you have to consider both their score on x and their score on y. So let's say that we say that a low y is a y less than 8, and a low x is an x less than 8. So of the people, if we're looking at this first category right here, low x and low y, of the people with low scores on x, x is less than 8, so these two people, how many have a y that is less than 8? Well, both of these people with an x less than 8 have a y less than 8. 1, 2, 2 goes here. Of the people with an x less than 8, or a low value for x, how many people have a high value for y, or y greater than or equal to 8? Well, these are our two people with a low value of x. None of them have a value that's greater than 8 for y, so that's why there's a 0 there. This next category, high x, x greater than or equal to 8, and a low y, y less than 8. If you go over here, we have two people that have an x that's greater than or equal to 8. We've got 8 and 15. How many of those people have a value for y that's less than 8? Well, this person valued greater than 8 for x, so they're high x. They have a 5 for y, which is less than 8. This person has a value that's actually greater than 8 for y, so they would be counted here. Whereas this person, high x, low y, counted here. This person, high x, high y, counted here. So I hope that helps you understand how you can take data that's initially designed for a parametric test, turn it into categories, count how many people are in those categories, frequency-based data, now appropriate for a chi-square nonparametric test. So there's two different types of chi-square tests. The first one is a chi-square test for goodness of fit. That's when we have a single variable. So that would be like this example right here, a chi-square test, goodness of fit. So when you have a chi-square test for goodness of fit, only one variable, and you're going to compare the observed frequencies in the sample, which is called FO, stands for frequency observed, to the expected frequencies, FE, frequency expected, based on the proportion of scores expected to be in each category under the null hypothesis. And this null hypothesis can be based on known population proportions. So your null would say the distribution of X in the sample is the same as the population, whereas the alternative would be the distribution of X in the sample is different from the population. Or your null hypothesis, which is the basis for your expected frequencies, your little FEs, that null hypothesis could be based on the proportion of scores expected to be in each category by chance. Or we're expecting under the null hypothesis that there's going to be an equal distribution of X across the groups. Whereas the alternative would be that there's not an equal distribution of X across the groups. So looking at this, if you see your data presented in a single row with multiple columns, you know that it's going to be a chi-square test for goodness of fit. Conversely, if you know you're just looking at the frequencies of one variable, it's a chi-square test for goodness of fit. Now on the knowledge check, I'm going to give you a description of the frequencies for each category, and you need to be able to put them into a matrix like you see here for the goodness of fit test. the practice problems will look like that as well. So you will get some practice before the knowledge check for doing something like that. Now, the chi-square test for independence is the kind of chi-square test that we use when we have two variables. And the chi-square test for independence compares the observed sample frequencies, so FO, for two variables to the expected frequencies under the null hypothesis, so your FE. Your null hypothesis in this case is similar to like the null hypothesis that we had for the correlation if you wrote it out in words instead of symbols. So the null hypothesis for the chi-square test for independence is that there's no relationship between the two variables. And we're really using the chi-square test for independence to make inferences about the relationship between two variables in the population, much like a correlation analysis. So each category represents a certain level of both variables. And just like before, with the chi-square test of goodness of fit, we're still meeting the assumption that each participant can only fall into one category. So if we go back and look at this example, where we had two variables, we have 1, 2, 3, 4 people, 2, 3, 4 people here. Each person is only in one category based on their level of X and their level of Y. So this would be the example that you could use a chi-square test for independence for. So when you have your data, you have multiple columns and you have multiple rows. And you need to be able to look at a description of data and place them into columns and rows. And one last thing, the null also says that X and Y are independent, hence the chi-square test for independence. If they're independent, they're not related. The alternative would be that there is a relationship between X and Y are dependent. So the chi-square formula, which would be step 3 of your hypothesis test, does not change depending on if you're doing a chi-square test for goodness of fit or a chi-square test for independence. The only difference in the calculation is how you go about finding the frequency expected under the null hypothesis. And I'll show you examples of how to do that. So the formula for chi-square is the same for both types of chi-square analysis, but again, the way you find the formula for frequency expected is different. And the degrees of freedom for step 2. So to find your critical value, you need to know your degrees of freedom. The formula for degrees of freedom is different for the chi-square test goodness of fit and the chi-square test independence. So for the chi-square test goodness of fit, you take the number of columns and subtract 1. So for this example, degrees of freedom would be 1. We have 2 columns, 2 minus 1 is 1. The degrees of freedom for the chi-square test of independence is equal to the number of columns minus 1 multiplied by the number of rows minus 1. So if we go back to this example, we have 2 columns and 2 rows. 2 minus 1 is 1. 2 minus 1 is still 1. 1 times 1 is 1. So our degrees of freedom would be 1 for that example. Now, I also want you to understand that if you get a large value for the chi-square test of goodness of fit, that tells you that there's a large discrepancy between the data and the null hypothesis. So much like when we were looking at the F distribution, your chi-square distribution is a positively skewed distribution, with 0 being the lowest value that you can get. 1 is the most typical value under the null hypothesis, and then as you start to get out into the extreme right side of the distribution, you're going to have values where there's a large discrepancy between the observed data and the expected data under the null hypothesis. Or in other words, a large difference between your FO, frequency observed in the data, and your frequencies expected under the null hypothesis. Now, for the chi-square test of independence, if you have a large value for that chi-square, that tells you that the variables are not independent of each other. Or in other words, there's a relationship between X and Y. So as your value for chi-square gets further out to the right of the distribution, that means there's a stronger relationship between X and Y. So let's go ahead and do an example for the chi-square test for goodness of fit. So I'm going to practice finding chi-square and testing the significance of chi-square. All right. So to see if the high cost of insurance for younger drivers is justified, That is, younger drivers have to pay more insurance because the justification is that they're in more accidents. A researcher selects a random sample of 300 accident reports from the DMV for 3 age-based categories of drivers. So we've got drivers under 20, drivers age 20 to 29, and drivers age 30 plus. So we feel like those are meaningful categories of drivers, and we count how many of these accident reports involved a person with each age. So if you add these together, 68 plus 92 plus 140, you'll get 300. We've split these 300 people that had an accident up into what age that they were. So what we're wanting to see is if the proportion of accidents is significantly different across age-based groups. So what we're trying to find out is if there is an equal proportion of accident havers in each of these categories. Now we're looking at this and we can already see that it's not equal. But what we're really trying to figure out is we're trying to use this sample to make inferences about the population and see if we expect that we wouldn't see this equality of accident reports based on age in the population, so that there needs to be differences more than we would expect to see just due to random chance. So for step 1, we're stating our hypotheses. Our null is that there is no difference in the population of accident reports across these age groups. So the distribution of accidents is not significantly different across the groups. It's equal. The alternative is that there are going to be expected to be differences in the number of accident havers for each age group in the population, or the distribution of accidents is significantly different across age groups, not equal. So step 2, you need to find your chi-square crit. And remember, you need to know your degrees of freedom to find that. And we know our alpha level is 0.05. So if we figure out our degrees of freedom, remember that's equal to the number of columns minus 1. So C minus 1 degrees of freedom. Well, we have 3 columns. 3 minus 1 is 2. 2 is our degrees of freedom. And I'll show you how I got this 5.999 from the table. So now we're going to be working with the chi-square distribution. And you can see, like I mentioned before, it's a positively skewed distribution as values get further out into the critical region. These represent values where the observed frequencies in our data are much different from the expected frequencies under the null hypothesis. So if we look at our degrees of freedom, which we found to be 3 minus 1 is 2, alpha level of 0.05, there's our 5.99. We don't have any 1 or 2-tailed tests because there's only one tail we care about. The tail that suggests there's a large discrepancy between the null hypothesis and the actual data that we have. So if I draw my critical region, got my positively skewed, these are my values for chi-square, my frequency. This represents 1, 0, and my critical region is 5.999, or 5.99. So my chi-square observed has to fall at 5.99 or above to reject the null hypothesis and say there are actually going to be expected to be differences in the age-based distribution of accident havers. Okay, moving on. So now we are going to do our calculations for chi-square. The first thing that we need to do before we can do any calculations, before we can use this formula, this chi-square equals the frequency observed minus frequency expected squared divided by the frequency expected for each group, we need to figure out our frequency expected. Now for the chi-square test for goodness of fit, when we're just under the null expecting equal proportions, we don't have any population proportions that we're basing this off of. There's 2 different ways that you can find your frequency expected. So you can find the proportion expected and multiply it by the sample size. That'll give you the frequency for each category. And to find the proportion expected, you just take 1 and divide it by the number of columns. Remember, proportion of 1 means everybody. Divide that proportion of 1 by the number of groups that you have. You can also find the frequency expected only when your null hypothesis is equal proportions by taking the sample size and dividing by the number of columns. I'll show you both ways for this because this way always works for chi-square test goodness of fit to find the expected frequency. This method only works when the null is expecting equal proportions. Okay, so let's go ahead and find our frequency expected under the null hypothesis that states that we have equal proportions in each group. So FE is equal to, so PE, which is 1 divided by C, multiplied by the sample size. So this becomes 1 divided by 3. We have 1, 2, 3 columns. And remember, our sample size is 300. So this becomes, so 1/3 is 0.3333 times 300. And you get 99.99. Now, you could also do this before you take the decimal here, just doing fractions. And you could do, 1 divided by 3 multiplied by 300 divided by 1. And if you did that, you would end up with 300 divided by 3, which is essentially what you're doing here. And I like that method a lot better when you can use it because here, FE is equal to 300 divided by 3 equals 100. You get a nice whole number that there's no rounding error involved. Because it's always nice when you add up. So if we put our frequency expecteds here, so younger than 20, to 29, and 30 plus. We've got 99.9, 99.9, 99.9. So whenever you are doing this, you want to put your frequency expected into a table that mimics the table with your frequency observed. So these are your observed frequencies from your data. And you'll see why that's a very important thing to do when I show you how to do the calculations for chi-square. But one way that you can check your work to make sure that you did your frequency expected correctly is to add these up, and you should get the same sample size that you had for the original sample. But if you add these up, you don't get that. If you take 99.99 and add it 3 times, you get n equals 299.97. I don't really like that, so I definitely prefer to do this strategy when I have equal proportions. So let's go ahead. I'm going to go ahead and write my frequency expected right below my observed frequencies. 100, 100, and 100. And in both cases, n is equal to 300. Now, keep in mind that when your null hypothesis is equal proportions for goodness of fit, you're going to have the same frequency in each column. This is basically saying if these 300 people were divided equally into the 3 columns, we would have 100 people in each group. So now let's go ahead and work through the analysis for chi-square, calculating the actual test statistic. So chi-square is equal to the sum of each observed frequency minus its respective expected frequency squared divided by the expected frequency. Now keep in mind, order of operations. First we'll do what's in parentheses, then we'll do the exponent, then we'll divide. And we have to do that for all 3 groups. We have to sum all of these up for each group. So if you think about a good way to check that you're doing the chi-square calculation correctly, you're going to have as many little equations, many calculations to sum up as there are groups. So let me go ahead and walk you through this calculation. It's tedious, but it's not too difficult. So each frequency observed minus its respective expected frequency, that value squared, and all of that divided by the expected frequency for that group. All right, so the first frequency observed for younger than 20 is 68. Their expected frequency is 100. Square that whole thing. Divided by 100, the expected frequency for that group. Plus, remember, we're going to sum all these together at the end. Well, the observed frequency for the 20 to 29 group was 92. The expected frequency was 100. Going to square that. Divide it by the expected frequency of 100. So you'll always have the same number here and the same number here. Granted, you're not going to have the same observed or expected frequency for all groups when we do the next type of goodness of fit test. All right, last one. We observed 140 accident havers in the 30 plus group minus what we expect under the null squared divided by what we expect under the null. So then the next step in calculations, we want to solve for the parentheses. So 68 minus 100 becomes negative 32. That's going to be squared divided by 100 plus 92 minus 100, negative 8 squared divided by 100 plus, all right, 140 minus 100, so 40 squared, still divided by 100. So negative 32 squared becomes 1024, still divide that by 100. Negative 8 squared becomes 64, still divide that by 100. And 40 squared becomes 1600. And we're going to divide that by 100. So then this becomes, after we divide all these by 100, 10.24 plus 0.64 plus 16. And you add those together, and you get 26.88 for your chi-square statistic. So that tells us there's quite a big amount of difference between the observed frequencies in our data and the frequencies we would expect if the null hypothesis was true and there was an equal number of people in each group. Think about the calculations for chi-square. If we're squaring all these values, remember, even a negative times a negative is not a positive, and a positive times a positive is a positive. So you're never going to have a negative value for chi-square. That's why we have a positively skewed sampling distribution when we are looking at our critical value here. So if we know that our chi-square is 26.88, that is like way out here. So our chi-square observed is 26.88. Definitely going to be rejecting that null. And our conclusion would be that the distribution of accidents is significantly different across groups. So basically, going back and restating the alternative hypothesis, because we rejected this, because there's a huge difference between what we would expect under the null and what we actually observed in our data. So think about this example that we just did, and put your critical thinking hat on and think about why this study is pretty flawed. I'll give you a second to think about it. You can even pause this video and think about it really hard. So what was wrong with this example? Well, it's pretty inaccurate to assume that the proportion of drivers is equal across age groups. So we were looking at the proportion of accident havers, assuming that there's an equal number of each age group of drivers in the population at large. So it's really not accurate to assume that the proportion of drivers is equal across age groups. And that's a problem because we were comparing the frequency of accidents by age to an inaccurate frequency of drivers by age. So instead of expecting equal proportions or frequencies of car accidents across age groups under the null, let's actually compare the age-based proportion of accidents to the age-based proportion of registered drivers. So if you're looking at this, we're like, oh wow, there are less accident havers younger than 20 than what we would expect under the null. But the null is incorrect because there's probably not an equal number of drivers under 20, drivers between age 20 and 29, and drivers that are 30 plus. So, of course, there's not going to be an equal number of accident havers in those groups because the number of drivers of those age ranges is not the same. So this gives us a nice example of when it's important to compare your observed frequencies in your data to the expected frequencies in the population, not just equal across groups, but to specific proportions from the population. So now we're doing an example with specific proportions instead of equal proportions. Because we know there's not going to be equality amongst these groups because there's not an equal number of drivers across these groups. So why would there be an equal number of accident havers across these groups? So everything is the same in the problem as before, only now we want to see if the age-based proportion of accidents, this, is significantly different from the age-based proportion of drivers, this right here. Now keep in mind that our observed data is turned into frequencies already. These are not proportions, these are frequencies. But we want to know what would be the frequency that we would expect if 16% of our sample were younger than 20, and 28% of our sample were between 20 and 29, and 56% of our sample were 30 plus. So you can turn those percentages into proportions, and then you can figure out how many people would be in each category in our data set if these proportions were true or the null was true. And we'll get to that in step 3. But step 1, the distribution of accidents is not significantly different from the distribution of registered drivers. This is different from saying the distribution of accidents is not significantly different across age groups. This was just saying it's not different at all. Now we're saying it's not different compared to what we would expect based on how many of these drivers are in each category in the population. Then the alternative, the distribution of accidents is significantly different from the distribution of registered drivers. So just as it's always been, the null, not significant difference, the alternative, there is a significant difference. And the critical value is the same for this. We still have C minus 1, degrees of freedom 2, and alpha level 0.05, and you'd find that in the table the same way that we did before. So now let's go ahead and work through step 3 of this hypothesis test. But keep in mind that we cannot use the N divided by C formula because that would give us 100 in each group. But we're not expecting that we're going to have an equal number in each group under the null hypothesis because now we're being more specific about the actual number of drivers in each category that are on the road. So we have to use the FE equals the proportion expected multiplied by N. But whereas before we had to calculate the proportion expected, remember we took the 1 and divided by the number of categories. Now that p-value is given to us. So 0.16 is the proportion of accident havers that we would expect to have in our sample if they equaled the proportion of drivers that are younger than 20. 0.28 is the proportion of accident havers between age 20 and 29 that we would expect to have in our sample if the proportion of accident havers was equal to the proportion of drivers between the age of 20 and 29. And 0.56 is the proportion of accident havers over 30 that we would expect to have in our sample if they were equal to the proportion of drivers over 30 in the population. So these are all these PE values. All of those are PE. Okay. So now let's go ahead and find our frequencies expected. So I'm going to just put all of my work into a table. So let's see. Again, these are FOs, frequency observed in the data, frequency expected under the null. So younger than 20, between age 20 and 29, and then 30 plus. Like I said before, you want your expected frequencies to be placed in a table that mimics your observed frequencies so your calculations are easier, because you need to find each expected frequency for each observed frequency in your data. All right, so 0.16, our expected proportion, multiplied by n, well, there's 300 people in our data set. So 0.16 times 300 gives you 48. So if the null is true and the proportion of accident havers is the same as the proportion of drivers for age younger than 20, we would expect to see 48 people in that category. So next one, PE for this one is 0.28 multiplied by 300. And we would expect to see 84 people in our sample of accident havers to be between age 20 and 29 if the null is true. And then finally, 0.56, the expected proportion based on the proportion of actual drivers that are 30 plus in the population times 300. You get 168. So we would expect that 168 people in our sample of accident havers would be 30 plus if that equaled the proportion of drivers in the population. Again, just because there's a difference between the expected and the observed frequencies doesn't mean that you can automatically reject the null. It has to be a substantial enough difference for us to be confident, if alpha is 0.05, 95% confident that that difference didn't occur just due to random chance. So let's go ahead and calculate our test statistic to see if it falls in our critical region. So the sum of each observed frequency subtracted by its respective expected frequency squared divided by the expected frequency. Again, each group. So we're going to have 3 of these because we have 3 groups. So the first one, younger than 20, we observed 68. We expected 48. Square that, divide by 48. The next group, 20 to 29, we observed 92. Under the null, we expected 84. Squared, divided by 84. Next group, 30 plus, we observed 140. We expected 168. Square that, divided by 168. So then this becomes, 68 minus 48 is 20. So 20 squared divided by 48 plus 92 minus 84 gives you 8 squared divided by 84. Add that to 140 minus 168 is negative 28 squared divided by 168. Now we need to solve for the exponent. So 20 squared is 400, still dividing by that 48. 8 squared, 64, dividing by 84. And 28 squared gives you 784. Negative 28 squared gives you 784, divided by 168. 400 divided by 48 gives you 8.3333. 64 divided by 84 gives you 0.7619. And then 784 divided by 168 gives you 4.6667. 4.6667. And you end up with a chi-square of 13.762. That's our final answer for step 3. So now we want to go see if this falls in our critical region, 13.762. And it totally does. 5.99. And our 13.762 tells us that there, in other words, if we're thinking about the alpha level and the sampling distribution, there's less than a 5% chance that we would get this much of a difference between our observed frequencies and our expected frequencies just due to random sampling error, just due to random chance. So we would reject the null, and we would say that results suggest that the distribution of accidents is significantly different from the distribution of registered drivers. A better way to say it is that there's a significant difference between the age-based distribution of drivers and the age-based distribution of accidents. You could simply just repeat your alternative hypothesis, but it's nice to include that this is an age-based distribution. So at this point, we know that there's a difference, but we don't necessarily know where the differences lie. And there is a way to do a post-hoc analysis in ChiSquare, but I'm not going to go into it. It's beyond the scope of this class. But I just want you to keep in mind that the ChiSquare is much like an ANOVA. So remember, an ANOVA, if you get a significant result, you know that there's at least one group that's significantly different, but you don't necessarily know which groups are significantly different from each other. Well, the same is the case in your ChiSquare for goodness of fit. But if you look at what we're really looking at in this study, we're wanting to see if younger drivers are involved in more accidents to justify that cost of insurance for younger drivers being higher. So in thinking about that, you can think about the fact that we got a significant result, even though, keep in mind, that the chi-square for this study was much smaller than the chi-square that we found when we were assuming that the distribution was equal. Although both are significant, once we're more accurate with the proportions in the population, our chi-square does shrink a little bit. So our observed data is a closer approximation of what we'd expect, because it compensates for the fact that there are less drivers that are younger than 20 on the road. Still rejecting null, still significant. We're really trying to make sense of this and say, is the cost of insurance for younger drivers justified? So to make sense of this analysis, we can look at the differences between the frequency observed and the frequency expected for each group. So the difference between the observed frequencies and the frequencies we would expect under the null hypothesis if we had this proportion of our sample in each group, these proportions. So let's go ahead and look at the frequency observed for accidents for drivers younger than 20, 68. Well, that frequency that we saw in our data is much more than we would expect to see if the proportion of accident havers reflected the proportion of drivers that were younger than 20 in our data set. So, in other words, the frequency observed of accidents for drivers younger than 20 is much more than the expected frequency for drivers younger than 20, based on how many drivers are younger than 20 in the population. Also, if you look at this, the actual frequency of accident havers between 20 and 29, frequency of people that had accidents that were between ages of 20 and 29, is larger than the frequency we would expect to see based on how many drivers are on the road between the age of 20 and 29. So drivers younger than 20 and drivers between ages of 20 and 29 actually have more accidents than what you would expect to see just due to chance in the population. So regardless of which pairs have significant differences between frequency observed and frequency expected, we know that the high cost of insurance for younger drivers is likely justified. They are overrepresented in the accident havers compared to their representation in the drivers at large. Then you can also see that the frequency observed for accidents for drivers 30 plus is less than the expected frequency for drivers 30 plus based on the distribution of drivers. So drivers that are 30 or older are actually having fewer accidents than expected under the null hypothesis, and they should probably pay less for insurance because there's less risk there. So I hope that shows you how you can take a significant finding for chi-square, compare the frequency observed to the frequency expected, and try to make sense of the data to answer the research questions that you have. Because typically you don't just want to know, is there a significant difference, but you want to know where those differences lie and what that means. Now let's move on to a chi-square test for independence, where you have two variables. So in this example, our two variables are IQ and sex. And we are wanting to see if there is a significant relationship between IQ and sex for a sample of 160 children aged 10. So we've got three different categories of IQ. The criteria are up here, boys and girls. Now, one way that you can, for the null hypothesis, you can state the null is the distribution of IQ scores is not significantly different for males and females. Or in other words, the distribution of Y is not significantly different based on X. So we typically want to assign the independent variable, variable X, to the left side here, so it'll be the basis for the rows, whereas the dependent variable, in this case IQ, is usually what distinguishes the columns. So X here, Y here. Remember, just like correlation, sometimes it's not clear which one's the independent and dependent variable, but in this example, it's pretty clear that sex is the independent variable. It comes first. You're a boy or a girl before you have an IQ. That would be your dependent variable. So another way that you can state the null is that there's no significant relationship between IQ and sex, or you could say IQ and sex are independent, hence chi-square test for independence. Then the alternative, the distribution of IQ scores is significantly different for males and females. The null says it's not significantly different. The alternative says it is significantly different. The alternative could also be stated as there's a significant relationship between IQ and sex, or IQ and sex are dependent. Whatever way you want to go about stating this, I am totally fine with, but I prefer the significant relationship between IQ and sex route because it's very familiar. It's something that we were doing for correlation as well. It makes sense to me. Here, for step 2, your critical value. First, you need to know your degrees of freedom. And remember, the degrees of freedom for a chi-square test of independence is equal to the number of columns minus 1 times the number of rows minus 1. Well, here we have 1, 2, 3 columns, so 3 minus 1 times 1, 2 rows, 2 minus 1. This becomes 2 times 1 is 2. And we already found the chi-square for degrees of freedom 2. You just find 2 under degrees of freedom. Then you look for alpha level of 0.05, and you'll find a chi-square crit of 5.99. Now there's two different ways that you can find the expected frequencies under the null hypothesis. The first way I'm going to show you is conceptual. It helps you understand why we get the expected frequencies that we do and why those expected frequencies represent no relationship between IQ and sex or between the independent and dependent variable. The second way that I'll show you how to do it is much more computational based. To me, it's a lot easier to do, and I would encourage you to do it the next way that I'm going to show you. I would say that for this slide, just pay attention and try to absorb the conceptual piece, and then for the next one, really pay attention because those are the calculations that you'll be doing. Okay. So the first thing that we want to do is create a new table and only keep the column and row totals. So I'm going to draw a new table that matches the previous table. So boys and girls. We've got a low IQ, an average IQ, and a high IQ. And we want to keep our marginal frequencies, or in other words, our column and row totals. So we have 80 boys, regardless of their IQ. We know we have 80 boys. We have 80 girls, despite looking at the differences in IQ. We have 30 people in our whole sample with a low IQ, not paying attention to their sex. 96 with an average IQ and 34 with a high IQ. You add these together and you get this. Conversely, add these together and you get this. So we've got equal number of boys and girls. 30 people have a low IQ, 96 average IQ, and 34 high. So what we're trying to do with our observed or our expected frequencies compared to what we observed in our sample. Remember, our expected frequencies are the frequencies under the null hypothesis. And the null hypothesis says that IQ and sex are not related and they're independent. So in other words, we want to make sure that there's an equal proportion of girls and boys in each IQ group to then test the null hypothesis. So if you think about it, if 30 out of 160 children have a low IQ, so 30 n equals 160, you can get this by adding 80 plus 80, 80 boys plus 80 girls, or 30 people with a low plus 96 with an average plus 34 with an high. Both way you go, you're going to get 160. So if 30 out of 160 people in our study, not thinking about sex, just 30 out of 160 with a low IQ, then we could say that 0.1875 would be the proportion that we would expect for boys and the proportion that we would expect for girls having a low IQ. So this is the PE for the low IQ. Well, let's do another color here. If 96 out of 160 have an average IQ, well, 96 divided by 160 gives you 0.60. And that would be the proportion that we would expect for boys and girls having an average IQ. So in other words, 60% of our sample, 96 out of 160, have an average IQ. So we want to make sure that 60% of the boys are put into the average IQ and 60% of the girls are placed in the category for average IQ under the null hypothesis. Here we know that 34 out of 160 had a high IQ. And 34 divided by 160 is 0.2125. So we would expect that, in other words, 21.25 of the boys and 21.25% of the girls, so 21.25% of the boys, 21.25% of the girls would have a high IQ if sex and IQ are independent, and the distribution of IQ scores is not significantly different for males and females. Or in other words, there's no significant relationship between IQ and sex. So when we do our calculations up here, we're still going to be doing, just like we did for goodness of fit, PE multiplied by N to figure out how many would be in each group if we had an equal distribution based on sex for IQ. So now that we know the proportions of our sample in each IQ group, we want to make sure that we have an equal proportion of girls and boys that are in each IQ group. So to make sure that the distribution is the same for males and females, we can multiply the proportions that we found by each row total to fill in the values for the frequency expected. So if 0.1875 is the proportion of people in our sample with a low IQ, then we want to make sure that 0.1875 of our boys, 80 of them, are in the low IQ group. And 0.1875 times 80 gives you 15. Now, do the same for girls. If 0.1875 is the proportion of total people with a low IQ, we want to make sure that the proportion of girls reflects that. Now in this case, we're going to consistently see the same numbers for each group, for boys and girls, because we have the same number of boys and the same number of girls. I'll do an example next where that will not be the case. So don't be thrown off if you see the same numbers here, because we have the same number of boys and the same number of girls, so we would expect the same number of boys and the same number of girls in each group. All right, next one. So if 60% of our entire sample has an average IQ, or in other words, a proportion of 0.60, multiplied by the number of boys, you end up with 48 boys. And 0.60 is the proportion for the entire sample multiplied by the number of girls, 48. The next one. 21.25% of our entire sample has a high IQ, or P equals 0.2125. So we want to make sure that 21.25% of the boys are placed in the high IQ category, and 0.2125 times 80 gives you 17. 80, 17. So If there's not a relationship between sex and IQ, then we would expect a sample with 160 people in it to have 15 boys and 15 girls with low IQ, 48 boys and 48 girls with an average IQ, and 17 boys and 17 girls with a high IQ. If we're just trying to figure out what we're expecting to find in our chi-square test, we can look at this and say 15 and 15 expected in all. That's pretty close to what we're observing here. 48 and 48, pretty close to both of these. 17, 17, pretty close to both of these. So I'm not anticipating a really high value for chi-square, but we still need to do the calculations to see if it's significant. But before we do that, now I'm going to show you the easier way to figure out your expected frequencies under the null hypothesis using this formula right here. The frequency for the column multiplied by the frequency for the row divided by the total sample size for the study. So for instance, this is relative to which specific cell you're looking at, which specific group. So for boys with a low IQ, the frequency column is 30, boys low IQ 30, and their frequency row, boys low IQ, is 80. And then you divide that by the total sample size for the study, which is equal to 160. So now let's go ahead and recreate this table. We've got low, average, and high, boys and girls. Those are our observed frequencies in our sample, and we're trying to figure out our expected frequencies. All right. So, for the first one, the frequency column for boys with a low IQ is 30 multiplied by the total number of boys, 80, divided by the sample size, 160. And 30 times 80 gives you 2,400. 2,400 divided by 160, and you end up with 15. Now here, we're going to have the same situation because we've got the same number of girls as we do boys. And we already know that that's 15. So the next one, the frequency column. So the total number of people in our sample with an average IQ, because now we're moving on over here. So we're looking at this column, 96. And if we're starting with boys with an average IQ, there's 80 boys. Total sample of 160. 96 times 80 gives you 7,680. Divided by 160, and you end up with 48. Same thing here. Now keep in mind, you won't get the same thing for both groups if you have a different sample size for both groups. Next one, high. Frequency column, total number of people with a high IQ is 34. Frequency row for the high boys is 80 boys, divided by 160, the sample size for the entire study. That gives you 2,720, so 2,720 divided by 160, and you end up with 17. Same thing here, 17. Check it out. These match the expected frequencies that I got using the other strategy. It's just that this strategy is a heck of a lot easier in my opinion. Okay, now let's go ahead and figure out the chi-square test for independence, the actual value. This is going to take a while because we have 6 different groups. So I will never do this type of analysis to you on the quiz. It's just too much. We don't have enough time. That being said, you may want to start looking at the analysis for your chi-square test early and not wait until after we do the practice problems in class to do it. All right, so the sum of each frequency observed minus its respective frequency expected squared divided by the frequency expected. Same formula that we used before. only finding the expected frequencies was different, the process is still the same. So for the boys with a low IQ, we observed a frequency of 18, expected a frequency of 15, squared, divided by expected frequency of 15. I'm going to go ahead and work from the top left to right down to the bottom left to right. So the next one. Boys with an average IQ. We observed 42. We expected 48. And 48. The next group. Boys with a high IQ. We observed 20. We expected 17. The next group, girls with a low IQ. We observed 12. We expected 15. Trying to find those differences between observed and expected. All right, next one. The girls with an average IQ. We observed 54, but we expected 48. Finally, girls with a high IQ. We observed 14. We expected 17. And there you go. So now this becomes, so we solve for the parentheses first, 18 minus 15, 3 squared over 15. 42 minus 48, so negative 6 squared over 48. 20 minus 17, so 3 squared over 17. 12 minus 15, so negative 3 squared, and that's over 15. 54 minus 48, so 6 squared over 48. And then finally, this value over here, 14 minus 17, negative 3, square that, divided by 17. Now we solve for the exponent, the next step, order of operations. So we have 9 divided by 15 plus 36 divided by 48 plus 9 divided by 17 plus 9 divided by 15 plus 36 divided by 48 plus 9 divided by 17. These numbers repeated themselves over again, but don't always expect that to happen in actual calculations. This just happened by chance. Okay, now let's go ahead and figure out. So 9 divided by 15 gives you 0.6. 36 divided by 48 gives you 0.75. And 9 divided by 17 gives you 0.5294. And since we have the same pattern happening again, so again, 9 divided by 15 gives you 0.6. 36 divided by 48 gives you 0.75. And 9 divided by 17 gives you 0.5294. You add all those together and you end up with a chi-square of 3.759. Finally, our chi-square value. Oh, hooray. So now we need to see, does 3.759 fall in the critical region? And it does not. It does not exceed 5.999. So if we drew this out, sometimes it helps to draw. 5.99. Our chi-square observed of 3.759 does not fall in this critical region. So we cannot reject the null. So, in our conclusion, we fail to reject the null hypothesis, and then results suggest there's not a significant relationship between IQ and sex. Or you could say, fail to reject the null hypothesis, the distribution of IQ scores is not significantly different for males and females. Or you could say, fail to reject the null hypothesis, IQ and sex are independent. Either way you want to state that is totally fine with me. So let's do one more chi-square test for independence example. This one is looking at a relationship between having allergies and whether or not you had pets in your home when you were a child. And we're looking at a sample of 120 college students. And we just ask them, how many pets did you have on average at any given time when you were growing up? And do you have allergies or not? So, do the data indicate there's a relationship between having pets as a child and resistance to allergies? So, in step one, we're saying there's no significant relationship between having animals as a child and resistance to allergies under the null. I'm just going to state it the way I like to state it. Then you could also state it, going back to these ways. You could say the distribution of having pets and having allergies is independent, or there is no difference in the distribution of allergies based on having pets. You could state it a lot of different ways, but I'm just going to stick to the way that I think is most straightforward. Is there a relationship or is there not a relationship? So under the null, there's no relationship. Under the alternative, there is a significant relationship between having animals and being resistant to allergies. All right, so in step two, we need to find our critical value. Degrees of freedom is equal to column minus 1 times number of rows minus 1. So in this case, we have 2 columns, 2 minus 1, and we have 3 rows. So 1 times 2 is 2. That's our degrees of freedom. We keep having the same degrees of freedom for these examples, but I already showed you how to find the critical value. Degrees of freedom 2, alpha level 0.05, it's 5.99. If we want to draw a nice little sketch of our critical region, 5.99, and there we go. Okay, next step. So I'm going to go ahead and use the frequency expected formula that I prefer. So FE is equal to, so frequency expected is equal to the frequency for the column multiplied by the frequency for the row for that group divided by the sample size. All right, so I'm going to go ahead and recreate this table, make it a little bit bigger so we have room for our calculations. We have 0 dogs or cats, 1 dogs or cats, and 2 plus. And then we have no allergies and allergies. All right. So for the first group, the people who had no pets, or no dogs and cats, no dandery pets, and had no allergies. So there are 90 people with no allergies, and there are 40 people who had 0 dogs or cats, and there's a total of 120 people in the sample. So 90 times 40 gives me 3,600. And 3,600 divided by 120 gives me an expected frequency of 30. Next group. So the number of people that have no allergies, 90, multiplied by the number of people, so the frequency for the row, of 1 dog or cat, so 60, divided by 120. 90 times 60 gives you 5,400. Divided by 120, and we would expect to see 45 people with 1 dog or cat who had no allergies if there's no relationship between having allergies and having pets. Next group. So the frequency column for no allergies is still 90. Frequency row for 2 plus dogs or cats is 20. Divided by the total sample size of 120. 90 multiplied by 20 gives you 1,800 divided by 120, and you end up with 15. Under the null hypothesis, we would expect to see 15 people with no allergies with 2 plus dogs or cats. Okay, next group. 0 dogs or cats with allergies. So the frequency column here is 30 people with allergies. And the frequency row, number of people with 0 dogs or cats, was 40, divided by the sample size of 120. 30 times 40 gives you 1,200, divided by 120, you get 10. Next group, people with allergies that had one dog or cat growing up. So the column total here is 30. The row total is 60. 60 people with one dog or cat. Sample size is 120. 30 multiplied by 60 gives you 1,800. Divide by the sample size of 120, and you end up with 15. Next one. 30 people with allergies multiplied by 20 people with 2 plus dogs or cats divided by 120. 30 times 20 gives you 600 divided by 120, and you have a frequency expected of 5 under the null hypothesis. Notice how we have different numbers for all the groups for the most part because we don't have an equal number of people with the number of animals. We have a different sample size for each of those groups. So we have different numbers for all of our expected frequencies. One way to check your work would be to make sure that your column and row totals are still the same after you find your expected frequencies. So 30 plus 45 plus 15 still gives you 90. 10 plus 5 plus 15 still gives you 30. 30 plus 10, going across now, is 40. 45 plus 15 is still 60. And 15 plus 5 is still 20. Add up 40, 60, and 20. You still have the same sample size. Because the whole point of this is trying to recreate the frequencies and that we would expect to see in our sample size based on the proportions that we would expect to see if there was no relationship whatsoever. So we should still have the same sample size for our expected and our observed frequencies. It's just we're rearranging these people into these categories under the assumption that the null hypothesis is true and there's no relationship between the two variables. So now moving on to calculating the actual chi-square statistic. Using chi-square is equal to the sum of each observed frequency subtracted by the expected frequency squared divided by the expected frequency. Okay, so now let's go ahead and figure out the value for chi-square based on all the numbers that we just found for the frequency expected and the observed frequencies in our data set. So I'm going to go from top to bottom and then top to bottom to the other side. All right, so let's see. Starting off with the top left group, no allergies, 0 dogs or cats. So we observed 22 people. We expected 30 under the null and divide that by 30. Next group, observed 50, so the no allergies, 1 dog or cat. Expected 45. Next group, no allergies, 2 plus dogs or cats. Observed 18. Expected 15. Next group, allergies, no dogs or cats. We observed 18. Expected 10. Next group, allergies, 1 dog or cat. We observed 10. We expected 15. And then finally, the people with allergies that had 2 or more dogs and cats. Observed 2, expected 5. Now let's solve for the parentheses. So 22 minus 30 gives you negative 8. We're going to square that eventually, divided by 30. 50 minus 45, 5 squared, divided by 45. 18 minus 15, 3 squared, divided by 15. 18 minus 10, 8 squared, divided by 10. 10 minus 15, negative 5 squared, divided by 15. And then 2 minus 5, negative 3 squared, divided by 5. Then when we solve for these squares, we have 64, 8 squared, divided by 30. 5 squared is 25, divided by 45. 3 squared, so 9, divided by 15. 8 squared, so 64, divided by 10. Negative 5 squared, so 25, divided by 15. And then negative 3 squared, or 9, divided by 5. So then we end up with, so 64 divided by 30 gives you 2.1333. Remember to round 4 places out as you go, and then at the end you round 3 places out. 25 divided by 45 gives you 0.5556. 9 divided by 15 gives you 0.6. 64 divided by 10 gives you 0.64. 25 divided by 15 gives you 1.6667. And then finally, 9 divided by 5 gives you 1.8. Add all those together, and you get 13.156 for chi-square. If you're one of those people like me who enjoy doing somewhat straightforward calculations, it makes you relaxed, you should be feeling really relaxed right now because that was a lot of calculating. Whew! A lot. It's easy to make mistakes on chi-square. That being said, I'm not going to give you anything that requires this much calculation on the quiz, but it is fair game for the knowledge check. It's important that you know how to go through this process to understand how the values that you get for chi-square in Excel come to be. Whew, all right. So now let's see if this chi-square of 13.156 is significant. Oh yeah, it is. Way out in the critical region. 13.156. That's our chi-square observed. So we're pretty confident that we can reject the null hypothesis and say that results suggest there's a significant relationship between having animals as a child and resistance to allergies. You could also say that having allergies having animals as a child and having allergies are dependent. Or you could say that the distribution of having allergies depends on the distribution of having pets. So we know that the findings are significant, but remember, that just tells us that there is a significant difference somewhere between the expected and the observed frequencies. So if we want to look at this and try to figure out what's going on here without doing a post hoc analysis, we can compare our expected frequencies, if there is no relationship, to the observed frequencies, knowing now that there is a relationship because we rejected the null because our chi-square was so large. So under the null hypothesis, if there was no relationship, there would be 30 people in our sample that don't have allergies when they don't have any pets. But we actually observed fewer than that. So there's fewer than expected people with no allergies when there are no cats or dogs. Conversely, there's more people than we would expect who have allergies when they don't have any cats or dogs. So just in looking at that, at the extreme end, no animals whatsoever, we would actually expect that there'd be more people that would have no allergies. There's actually fewer people that have allergies and more people than we would expect that have allergies when they don't have any cats or dogs. So far, this is supporting that maybe when you don't have any cats or dogs, you're more prone to have allergies than to not have allergies. If we look on the other extreme end of this distribution, those who had 2 or more dogs or cats, well, 18 of them had no allergies, but we would actually expect fewer of them to have no allergies if the null hypothesis was true and there was no relationship. Then on this end of the distribution, there's only 2 people in our sample that have allergies when they had 2 or more cats and dogs, and we would actually expect there to be more than that, 5, if the null was true. So this also supports that there's actually fewer people with allergies than what we would expect to see if there was no relationship between allergies and how many pets that you have. So far, it looks like this is supporting the hypothesis that having animals tends to result in less likely to have allergies. There's a relationship there. But just like correlation, it's not causal. Just because there's a relationship does not mean that it's a true causal pathway. It could be the other way around. It could be that those who have allergies probably had parents that had allergies and are therefore less likely to have pets in the home. Or there could be a whole host of other factors related to both allergies and the likelihood of having pets that could result in this relationship. So I hope that this class has been enjoyable for you and you've learned a lot and that you have a strong finish this semester.